Alright, let's start with section 3.3, solving by elimination. If you recall, in the last section we learned the method called substitution method. This time we learned the elimination method. Now both methods are used to solve a system of two equations with two variables. Now remember, a system of two equations with two variables, we can use graphing, we can use the substitution method. Now we can use the elimination method to solve the solution, which can be the ordered pair where both lines intersect, or when the case both lines are parallels, or when the case when both lines intersect each other's, or overlap each other's. Okay, basically they are the same lines. Alright, it's very similar. Just using different methods to solve a system of two equations with two variables. Now, you may be wondering why we'll learn another method to solve, right? Why just use the substitution? Why do we need to learn the elimination method? Now, depend on the given, the form of the equations, the given, and a lot of time or sometimes this elimination method is simpler to apply. So depend on what the equation are given, the form or the format. And sometimes using the elimination is easier, more convenient, faster than the substitution method. That's why this method we got to learn is very useful, very helpful, and very powerful too. Now, I have the outlines here, which from the book it say that to use the elimination method to solve systems of two equations, there are 6 steps. First, write both equations in the form ax plus by equal to c. So we don't need to solve for y. So if the equations is given in terms of y equal to something on the right, so y on the left hand side, that means you need to convert that to the form ax plus by equals c. A, B, C's are constants. Step 2, clear any decimals or fractions. Step 3, choose a variable to eliminate. Step 4, make the chosen variable's terms opposites by multiplying one or both equations by appropriate numbers if necessary. 5, eliminate a variable by adding the respective size of the equations and then solve for the remaining variable. And lastly, substitute in either of the original equations to find the value of the other variable. Step 6 is very similar to the last step in the substitution methods, where we found one variable and then you took that variable and substitute to the other equation, substitute the variable in the other equation to solve the remaining variable. Okay, and then again, it also has the special cases. So when solving a system of two linear equations in two variables, if a false equation is obtained such that 0 equals 7, then the system has no solution. The system is inconsistent and the equations are independent. So if you're given a system of two equations, okay, and a system of equations like f of x, g of x, okay, and you solve for b2 and you get 0 equals 7. So all the variables has been eliminated. The remaining of the equation is constant equal constant, but this time 0 cannot equal 7. It's impossible. So we said false. So that means when you see that, you will say that the system has no solution. Actually, it's something like this, okay? No solution. If you see something like this, think about this. The system has no solution because the two lines do not intersect each other. So no solution. The system is inconsistent. Okay, no solution means inconsistent. And the equations are dependent. Sorry, the equations are independent. That's what I like. It's not weird. So, and equations are independent. They're independent because they don't represent the same line. They're different lines. So, second special case, if a true equation is obtained, such as 0 equals 0, then the graph has an infinite number of solutions. The system is consistent and the equations are dependent. Alright, so similarly, you're given a system of two equations, you solve it, simplify for it, and all the variables, x and y, are gone, or eliminated. All you get is a constant equal a constant. Now this time 0 equals 0. It's true. So it's a true statement. So that means that's when you would say the system has infinite number of solutions. The system is consistent and the equations are dependent. When this happens, is actually this case. Okay? Where two equations that represent the two lines and they're actually the same line. It's just the equations are written in a different format or shapes, but actually they both represent the same line or same equations. So in that case, you would have infinitely many solutions, and then you would say they're consistent. Consistent because these two lines do intersect, right? When they overlap, they intersect at every point. That's why there are infinitely many solutions. And that's why it's consistent. Consistent means there is at least one or more solution. And then lastly, you say the equations are dependent. Dependent because the two equations represent same line, one line. Okay? That's what we call dependent. So those are the concepts before we talk about example.